Hi, my name is Arnav Saxena, and I'm going to be talking about Lab3 today. Introduction. So for this experiment, our goal was to measure the distance dependence of the magnetic field due to a small bar magnet, and then compare this to the dependence predicted by the equations magnetic fields derived from the Biot-Savart law and also from a computational model. The physics principles that we were studying with this experiment were magnetic field behavior of both Earth's magnetic field and the local magnetic field from the bar magnet, and then also magnetic field equations according to the Biot-Savart law for on and off axis and distance dependence based on these. So our materials that we used were a bar magnet, a smartphone with a magnetometer app to measure magnetic field, a meter stick, another additional meter stick or ruler, a few pieces of tape, and also the Excel spreadsheet used to graph and derive the data that we collected. So for compensating for magnetic north, this was the first procedure that we had to do in order to set up our experiment. And so for this experiment, we took our smartphone and we superimposed it along the bar magnet's field along with Earth's magnetic field. And we balanced this along a meter stick or a ruler, which shows how the smartphone was aligned with Earth's magnetic north and south axis, which is vertical to the smartphone, and then the east to west axis, which was horizontal and based on the meter stick. And so in my case, the net magnetic field was around 49.23 microteslas, which is approximately 49 microteslas as calculated due to the longitude and latitude of Atlanta, Georgia, which is my location. And for the next step, we wanted to find the actual location of the magnetometer sensor that was used according with the specifications of our smartphone. So with my smartphone, we measured that the position along the phone perpendicular to the axis, where the absolute value of the x component is at a maximum and the absolute value of the y component is at a minimum. And then similarly for the on-axis, we wanted to find the maximum and the absolute value of the y component, and then the minimum of the absolute value of the x component. And in doing this and adding the bar magnet as well, we could measure out the distance and see that the position of the sensor was around the bottom left side of my smartphone. Now, in order to collect our data, we basically assigned our smartphone to move a certain distance of however many meters in order to obtain the actual amount of microteslas that we needed. So in this case, we measured in intervals of 20, 70, 120, 170, and 220 microteslas. And as you can see from the data shown, you can derive an equation and also a line of best fit based on this, which takes in the actual average distance found to use for the specific amount of microteslas and also for the average magnetic field. So in this equation, we can see that we wanted to derive the ln of k and ln of r values, as well as the n value found from the equation of line of best fit. So in order to calculate the magnetic moment, we can use this and set these values into the k times rn equation, which equals the magnetic field, and also set this to the actual magnetic field of the bar magnet. And then solving for mu, which corresponds to magnetic moment, we can get around 2.03 amp meters squared. And then using this magnetic moment, we can then plug this into our computational model. And assuming that the magnetic meter is far away from the magnet, which measures a near zero magnetic field in the x direction, and also this measured x component will increase as it moves closer, since it's dependent on distance. So for our coding, basically plugged in the magnitude of mu, which is 2.03, and then we set up a series of equations to find the actual the magnetic field. And using this, we assigned our scale and distance values and also our different observation axes based on specific vectors that corresponded to either on-axis or perpendicular to axis locations. And then using our off-axis field data from the data shown here, we then included this distance as well to find the 45-degree magnetic field distance and also the magnitude. So here, based on the coding, you can see that our locations for each of the magnetic field vectors based on the axis and the perpendicular locations, as well as the one found at 45 degrees. Now this value isn't as close as it was to the ones found based on the experimental values, and this is probably due to human error and the desired differences based on simply measuring the magnetic fields based on the magnetic. For our conclusions, if we hadn't oriented our experiment to compensate for magnetic north, then that would have meant that the component of Earth's field would also affect our results in the magnetometer, which meant that the Y component specifically would probably add on to or somehow affect the magnetic field that we calculated, since we weren't specifically looking at the perpendicular axis. If we were to stick two identical magnets together end to end, then this would probably increase the magnetic field, since we're taking into account now two bar magnets and also two dipoles, which will stack and then also increase their magnitude based on the magnetic field that we were trying to calculate.